Planetary Defense Coordination Office comes from a national strategy, an action plan that was released by our White House now 3 years ago, and it guides our efforts for improving and increasing our capabilities to address such a hazard. The Planetary Defense strategy here at NASA has 5 different elements, and we work both projects and on working groups and teams to address all of these elements. First and foremost, most important is to find these objects, find them early, give us the maximum amount of time available to be able to respond and address an impact hazard. Then a number of our projects sponsored by NASA are working to better characterize this population of asteroids and comets that come into the inner solar system and over time represent a hazard to the Earth. A good deal of our time is spent in planning and coordinating our activities and potential response options, both within the U.S. interagency and with our international counterparts at other space agencies around the world, the European Space Agency, the JAXA, Japanese Space Exploration Agency, and also Roscosmos and the Chinese National Space Agency as well. Then finally work on plans and technologies that could be used to mitigate an asteroid while still in space so that Earth never suffers such an impact again. And I'll talk a lot more about this area later on in my briefing, and then our capabilities needed to assess our progress and success at finding this population of objects and being able to do something about them. Our progress to date in finding the population of nearest asteroids, we just recently crossed, having found 27,000 near-Earth asteroids of all sizes. About almost 10,000 now of what we have found are asteroids that are larger than 140 meters in size, size of a small stadium. And we have that threshold that we are looking for objects of 140 meters and larger in size, because that's a threshold at which the effects of such an impact could have severe regional damage and represent really a national threat to both our economic and human welfare security with asteroids that severe. Of course, smaller asteroids can survive the entry through the atmosphere and also impact and do a lot of damage if they hit in the wrong place, but it would not necessarily be a national existential threat at smaller sizes. Almost 900 of them now found are even larger than that, but so far none of these found have a significant chance of impacting the Earth over the next century. But we are tracking a little over 2,200 of them that fall in a category we call potentially hazardous asteroids to the Earth. These are asteroids that over time their orbits bring them within 5 million miles, 7 million kilometers of 7.5 million kilometers of the Earth's orbit. So we want to keep track of those and look for any potential impact events over time. As I said, our Congress here in the U.S. has tasked us with finding these 140 meter and larger asteroids That's referred to as the George E. Brown NEO survey goal, named after a significant chairman of our House Science Committee in setting up that goal for us. Actually, a advocate of NASA starting this whole program in the 90s. And so, of that population, why should we worry about them? And most people don't understand that we have asteroids that come close to the Earth all the time. And I show here numbers within that came within one lunar distance of the Earth in 2020. Now these are most of them, thankfully, very small asteroids, of which most of them, if they were to have impacted the Earth, our atmosphere would have disintegrated them. But there are several that are significant size. One was estimated to be as large as 200 meters in size, and that would be a bad day just about anywhere it impacted for us. And 30 were estimated to be as large as 20 meters in size. That is of interest because the Chelyabinsk event back in February of 2013 that resulted in an airburst over the Russian city of Chelyabinsk and surrounding cities, and caused a great deal of damage to buildings and injured over 1,600 people. So events of that size, while not national disasters, are certainly things that we would want to warn of if we found them ahead of time. 7 of these objects actually came closer than the geosynchronous satellite belt, closer than our communications and TV satellites. Significant records were set of the closest approaches we had ever seen in the time that our program has been in existence. On August, this, again, small asteroid, 5 meters or so in size, came within 3,000 kilometers of the Earth's surface, discovered by one of the projects we support. But then just 3 months later, something came even closer. This slightly larger object, maybe as much as 10 meters in size, passed above the Earth's surface at only 375 kilometers. And that is about the same altitude of the International Space Station. So that opened our eyes a little bit to see something that size come through the low Earth orbit regime. Now, small asteroids do impact the Earth all the time. This chart shows that data has been collected over a period of about 30 years of impacts in our atmosphere of objects estimated to be at least a meter or larger in size. There's some almost 900 events that are in our records, and some of them quite significant. If we use a measurement here of a nuclear explosive device in the orange, the events that have occurred in the last actually shorter period, about 20 years, these have all occurred, almost a little over a dozen of them, of events that are larger than a nuclear explosion. And Chelyabinsk, I already talked to you about, has been the largest recorded energy release of about 450 kilotons of energy, kilotons of TNT, and then and also an event back in 2018 that took place in the Bering Sea, and so therefore wasn't widely observed. This was an event of about 50 kilotons. So There's a lot of objects we know about out there, but we know there's a lot more than we have so far in our catalog. We estimate, based on population studies, that we only currently know of about 40% of these 140-meter and larger objects, and that is data that's been collected over a period of over 20 years now. Our current rate of discovery of about 500 a year. It will take us another 30 years with the current assets we have. So a mission that NASA is now approved for development, our near-Earth object surveillance mission, is to develop and launch a space-based infrared telescope that's specifically designed to detect, track, and characterize the near-Earth asteroid population. And once it is launched and into operation within 5 years, it will find 2/3 of that population, and a goal within 10 years of finding over 90%. The nice thing about the infrared signature detecting in the infrared is you can make more direct measurement of the sizes of the objects as you discover them and observe them. You don't require other assets to help you with the characterization of the objects. It will also deliver tracklets of astrometric observations to the Minor Planet Center, just as our current surveys do, and that data will all be available then worldwide. This, as I said, this project has been approved for preliminary design phase this last June, and if the President's budget request that is currently with our Congress, starting in FY22, that budget profile is funded, we'll be able to launch the NEO Surveyor in 2026. So now let me focus now on another mission that we have that's been in development for a while, and we're getting to the really exciting part here, in that we'll be launching in less than 5 weeks the double asteroid redirection test. In our strategy element, it's clearly within the mitigation sector. It's our first full-scale flight demonstration of a asteroid deflection technology technique called the kinetic impactor. DART, of course, fits into our overall national strategy here in the U.S. With these 3 goals as part of that strategy. Goal 3 being to test NEO deflection and disruption capabilities, but also has elements within our improvement of our NEO characterization and effects modeling, and providing integrated information of those results, and an increasing international cooperation among countries around the world in this endeavor of planetary defense, and that we have elements of the mission that are contributed by other countries, and it's part of a collaborative effort that we have with the European Space Agency called the Asteroid Impact Deflection Assessment. And ESA itself is developing a mission called HERA that will go to the same asteroid system that DART is bound for a more detailed post-impact assessment and detailed study of the Dynamo system. DART, now there's no known asteroid that's an actual impact at risk to the Earth right now. The major risk we have right now is the undiscovered population, but we are testing this kinetic impact capability so that if an object does pop up that is an impact risk, we will have at least one tool at our disposal that might be used to deflect it in space. The launch period for DART opens here, as I said, in 5 weeks. November 25th, it will launch out of the Vandenberg Space Force Base out in California on a Falcon 9 procured from SpaceX. The spacecraft carries a CubeSat with it that has been contributed by the Italian space agency called Lucia Cube, which it will deploy a few days before the impact, and the Lucia Cube will follow the DART spacecraft in, because, of course, when it impacts, it is gone. It will be imaging all the way to the impact point, but Lucia Cube is designed to collect images of the impact and the ejector plume that results from it, and a more complete imaging record of the Dimorphos, the moon of this binary asteroid system that we're using as the target. The Didymos binary system has been closely observed from Earth-based observations for several years, so that we understand as much as we can about it prior to this impact, which will occur a little less than a year from now, late September of 2022. And then Earth-based observations will be taken to determine the effects that we've had on this orbit of this moon. So these are the mission requirements. Of course, we have to impact Dimorphos with the spacecraft. That will change the orbital period of the binary about the larger asteroid. And then we have to measure that period change to see what the effect of the impactor was on the orbital period, and also make a measurement of the beta factor, and that is, what is the enhancement of force that is created by the ejecta that is blown off from the surface of the asteroid by the impact. That crater that is made by the impactor enhances the force enhancement factor. What's interesting about this mission, as opposed to a lot of planetary science missions we do, is that the spacecraft is done in the first act, so to speak. When the spacecraft impacts the asteroid, its work is done, but a good deal of the work for finding out exactly the effect that we had is done after the spacecraft is gone. Kind of a size, relative size of the moon, Dimorphos, and the main asteroid, Didymos, is about 800 meters across, or about half a mile in English terms. So this is a little animation about the event. Dimorphos is orbiting its primary Didymos. It's been observed by Earth-based observations over time. And then the DART spacecraft comes in, drops off the Lucia Cube, then impacts the asteroid and Lucia Cube images as it passes on through the system. But that impact will decrease the velocity of the moon about the primary asteroid, and that causes the orbit to drop down because of the gravity, and actually increases the speed, orbital period of the orbit. So it decreases the speed of the asteroid, but reduces the period of the orbit, I should say, and increases the number of orbits over time. The orbital period of Dimorphos is about 12 hours, and we're drop it by about 10 minutes is what we're expecting. How do we know all this? Didymos is an eclipse, what we call an eclipsing binary, and as the moon passes behind and in front of the larger asteroid, the light curve changes. You see these dips in the light curve when it comes in front and then goes behind. And so we know the period based upon the distance between those features in the light curve, and that will change after the impact. The time between the light curve features will decrease, and so that's how we will measure how we've changed the orbit. And that's done by a host of ground-based observatories around the world. Just a diagram of the DART spacecraft, and the Draco instrument is a primary, really the only instrument on board DART. It does both the optical navigation and the imaging as we come into impact. We don't know too much about the moon of Didymos. It appears, even in the largest ground-based telescopes, as a dot of light in the sky. We do have a little bit of radar on it, but it'll be this is one of the challenging things of the mission, is that it is closing so fast, and the lag in time is so long that you can't joystick it from the ground. It has to have autonomous navigation of the spacecraft. And we will only pick up the moon about an hour before the impact, and it needs to guide itself then into the moon. So it's a challenge from a technology autonomous navigation standpoint. There's just some images of the buildup of the spacecraft out at the Applied Physics Lab, the lead institute for the DART mission. We had some challenges over the last year due to COVID, and that, first of all, some of the components were delivered late, and also had to revise our processes for integration and test of the spacecraft, because you had to limit the number of people that could be in a clean room at the same time. Normally you see half a dozen people just watching the operation gathered around. So in this case, they had to keep their distance as best they could, and do a lot of the observing of the integration and testing from the control room, or even remotely from their laptops. Installation of our new technology, high gain antenna. This is different than high gain antennas you may be used to seeing. It's a lot smaller, and of course then lighter weight. We have also testing a new ion propulsion system, xenon propulsion system. It's not required for this mission. It's just an opportunity to test it to be used in future missions and planetary science, planetary missions. Testing, thermal vac testing, installation of our solar arrays. Finally, this last May, delivered a few months late because of COVID impacts, and then installation of our instrument in June. And then the final component to come and be installed just a month ago was the CubeSat from the Italian space agencies. And these guys are proud to have their CubeSat installed. And now that is all blanketed up and shipped to the launch site. We shipped to Vandenberg a little over 2 weeks ago, and it's doing its testing out there. We'll move over to the SpaceX pad this next week, and encapsulation and final preparations for launch on the late evening on the 23rd of November out at Vandenberg, early morning here on the East Coast and mid-morning in Europe. There's a nice video here of it that I'll just leave you with because I know I'm out of time. And with that, I will be glad to take any questions that you have.
Yeah, thank you so much. So, Brandon? Oh.
So if anyone has any questions, no,
You're just talking to this or Mike?
Yes.
Okay. Sure. So yeah, thank you for the support for SGC and for speaking to us tonight or this morning for you. I was curious about the OSIRIS-REx mission that did the sample acquisition of asteroid Bennu last year. Was there any way to measure if the asteroid Bennu's orbit changed from that mission? And then I also wanted to ask if there were any things learned from that mission that's informing the DART mission.
Yeah, well, in answer to your first question is, yeah, we did take that into account, whether there would be any change for that mission. I should say up front that OSIRIS-REx is not part of the planetary defense portfolio. It's another part of planetary science, but I know the people that, that are doing it. The sample collection made no significant change at all, no detectable change of the orbit of Bennu. But both the data collected, imaging data, and other collected data in OSIRIS's time around Bennu, provides us a lot of characterization of that particular asteroid, but that can also be applied to understanding other near-Earth asteroids. We know now very up close and personal what Bennu looks like, and we've observed it remotely, so we can compare then if we see other asteroids that look from a remote sensing standpoint a lot like Bennu, then we know that the composition is probably about the same as Bennu, and that informs us as to what we might be dealing with if it's an asteroid that is an impact hazard to the Earth. All of our, we have a number of small bodies missions going on, and they will all provide us good data that we can then put into our models of near-Earth asteroids. So planetary defense, I like to refer to planetary defense as applied planetary science, and that it is closely related and quite informed by small bodies planetary science.
I guess you can hear me. I was just wondering about, maybe it's just a very naive question, but how does it work, like internationally speaking, when you see and when you detect an asteroid that could potentially be very impactful on the Earth? How does it work between the different agencies, and how can you manage the problem at international level? Is it like, I don't know, the most powerful that would deflect it and some others would help, or something like this?
It all depends on the scenario, but another big element of planetary defense is working with the international community and in collaboration under the United Nations Committee on Peaceful Uses of Outer Space. There have been negotiations that led to the establishment of the International Asteroid Warning Network, where observers, orbit modelers around the world participate in the International Asteroid Warning Network. In fact, we had a meeting of the network just earlier this week. collaborating on detecting, tracking, and characterizing near-Earth asteroids, and also a companion establishment of what we call the Space Mission Planning and Advisory Group. And this is a forum for the world's space agencies from all nations and offices and space agencies from all nations to work collaborative on technologies and techniques that could be used to deflect an asteroid in space. Meeting of what we call Same Page, Space Mission Planning Advisory Group, Same Page, just occurred last week. There's over 18 space agencies and offices from many nations that participate in this work.
Anyone else have one final question?
Thank you. Yes. So for ground-based observatories, we know that now satellite constellations are impacting a lot astronomy, especially that is ground-based. So I was wondering how much the increasing crowding of terrestrial orbits, low Earth orbit in particular, is impacting planetary defense, or if it's not impacting it now, if it can slow down the rates of discovery, because you say that in 10 years, you intend to detect 90% of remaining not undetected near-Earth objects, but in 10 years, we will also have hundreds of thousands of satellites more in orbit. So how does this impact near-Earth object detections? And if
well, let me put it this way: it doesn't help.
Working on that.
Yeah, let me put it this way: it doesn't help that we have all these satellites that will enter in the field of view of our ground-based telescopes. It's something we have to deal with today with the population that's up there, of satellites when they are reflecting sunlight across our fields of view and eliminate the usefulness of portions of the images. The more there are up there, the more that will happen. We've estimated that if, for instance, this 30,000 constellation goes up that's being talked about, that probably every image that we take of the sky will have one of those satellites, spacecraft in it. And so every image we take will be affected, as opposed to maybe 1 out of 100 images right now. So it won't stop us from doing it, but it may affect how quickly we find this population from the ground. But that's one of the reasons, another good reason for us doing this space-based infrared telescope. It will be positioned out at the Earth-Sun L1 point, and no Earth constellations orbiting the Earth will affect it.
All right, we have time for one last quick question. And here we go.
Hi. So I wanted to know that so most of the asteroids that near objects are there, they are from the sunlit side, so we cannot see them really. And now that so how is the PDCO going to be tackling that? Like, is there any scope for using deep space telescopes, or with Artemis developing more lunar technologies, is there a scope for using lunar telescopes and observatories?
Well, any asteroid that is going to be an impact hazard to the Earth has to cross the Earth's orbit at some point. So part of its orbit will not be on the sunlit side; it will be in the night sky. So there are, even from ground-based observatories, there are always opportunities to detect and track these objects. An impact by a significant sized one is pretty rare, and as long as you're looking, you will pick those objects up over time. But so they don't, if they're going to be a threat to the Earth, they're not always going to be on the sunlit side, and so they can be detected. But it's another good reason to have space-based capabilities doing this. From the L1 point, we'll be able to observe these asteroids for a longer period of time than they can be observed from Earth-based observatories.
All right. Thank you so much. That's all the time we had for questions. Thank you again, Lindley, for joining us.
You're welcome. It's a pleasure to do it. Good luck to all of you in your endeavors. And as I often like to say, planetary defense is a team sport. It takes people from all walks of life and expertise to join the effort. Thank you very much. Good day.
Where do you leave?
Mic is off. Mic is off. Mic is off.